Okay, so welcome back, everybody. We're simply very much looking forward to the sixth lecture in the series. Well, the stage is yours.
I guess I have to not talk until I'm wearing this thing. So, as I remarked at the end yesterday, there's a threefold analogy: Rindler space, de Sitter, black hole. Rindler space is definitely the least important of the three, and the reason is that the problem of a uniformly accelerated observer is at least artificial. It's a little artificial. But Rindler space is also the easiest to understand of the three. That was why I explained it first. The reason it's the easiest to understand of the three is that in Rindler space, the important state is just the vacuum. And you already knew its main properties, namely minimum energy and Poincare invariance. So I didn't have to convince you of any of that. De Sitter space, the important state is what I called the Sitter psi ds, and it had two important properties. One is that it is de Sitter invariant, and the other is that it can be created by an integral on a hemisphere. So in de Sitter space, we have to explain this to just get to the starting point in Minkowski space where you already know about the vacuum state. However, once we did have this, the formal arguments to get the same picture in de Sitter space as in Rindler space, the formal arguments are the same. I might have gone through them a little bit too fast yesterday, and you may or may not have reviewed it in my lecture notes as I suggested you do. But in any case, they're the same arguments as in Rindler space. Now for the black hole, there's the same story. So there's a special state for the black hole, which I like to call the Hartle-Hawking Israel state. Some people call it that. And it has, again, two properties. One, it's time translation invariant. Well, it has the symmetries, but the only important symmetry is time translation symmetry, Schwarzschild time. It also has rotation symmetry. That's more trivial. But it has time translation symmetry, but it also can be created by, in a way I'll explain, by a path integral in half of the space. So that'll be the analog of this relation for de Sitter space and of the properties of the Minkowski space vacuum in the case of Rindler space. And just as for de Sitter space, once we define the state and understand its two properties, completing the threefold analogy between Rindler space, de Sitter space, and the black hole, the remaining steps, once we know this much, are exactly the same as they were for Rindler space. I'll attempt to be patient and to go over the steps in slightly more detail today than I was yesterday with de Sitter space. And also, the pictures are easier to draw because the main story is happening in a two-manifold, whereas yesterday it was happening in a four-manifold. And I don't know if you understood the words I was giving, but the pictures were probably hard to understand. Anyway, that's the story of what we'll be trying to do in roughly the next half hour, I guess. So we'll aim to understand what you could also call the thermofield double state of a black hole. So remember that the Schwarzschild black hole has got this metric in Lorentz signature. And then we continue to Euclidean space, and we have the same metric, except with the plus sign for the first term. I won't write everything out. The rest is the same. And so the state we want to construct, well, first I'll tell you what the correlation functions are in the state. And then that'll just be notation. That won't really prove it's a quantum state. Then we have to prove that there is a quantum state with those correlation functions. So I'll use notation as if we know that these are correlation functions in a state, but it will just be notation. So O is any local operator. It could be an elementary field, but it doesn't have to be. And the Hartle-Hawking Israel state is supposed to have the property that expectations in that state are just given by expectations in the Euclidean Schwarzschild solution. Except I'll call this state psi prime because it's unnormalized. On the right-hand side, I don't normalize the path integral. So the right-hand side is simply the path integral in the Euclidean Schwarzschild solution with insertions of whatever operators you want to insert. So if you want a normalized Hartle-Hawking Israel state, it's just this unnormalized one divided by a normalization factor. And the normalization factor is the Euclidean Schwarzschild path integral with no operator insertions. So, assuming that there is a quantum state with these correlation functions, what does it describe? Well, so if there is such a state, then far from the black hole, it describes, well, thermal equilibrium of radiation, which if in pure gravity would just mean gravitational waves, but maybe we have photons as well, at the Hawking temperature. Why do I say that? I say that because the Euclidean Schwarzschild solution far away from the black hole is just R3 times a circle, where the circle has a circumference which is beta Hawking, the inverse of the Hawking temperature. And presumably from our study of quantum statistical mechanics, we're familiar with the fact that correlations on R3 times a circle are thermal correlation functions at the inverse temperature given by the circumference. So far from the black hole, it describes thermal equilibrium of radiation, but since it's a time-independent state, somehow that radiation is in equilibrium with the black hole. Of course, in an asymptotically flat spacetime, this is unstable equilibrium, as I've explained. We could modify the problem, well, okay. I wrote here the asymptotically flat Schwarzschild solution, but nothing I've said would have been different if I'd written down the asymptotically ADS Schwarzschild solution. And then, as I also explained yesterday, if the temperature is high enough, this would actually be stable equilibrium of radiation with the black hole. Now, so as before, we want to know that there is a state with these correlation functions. And the strategy to construct this state is the same as it was yesterday. Namely, we do a path integral on half of the space. Well, but the only slight subtlety is to explain what I mean by half of the space. So, I'm going to take the symmetry TE going to minus TE and look at the fixed point set of that symmetry. But you have to remember that TE is a periodic variable with period 8 pi gm. So the fixed point set is really that TE is 0 or 4 pi gm. To understand best what's going on, I'm going to draw a two-dimensional picture where I suppress the angles. We keep the angles on the two-sphere fixed. And I'm just going to plot R and TE. So what kind of two-manifold is parameterized by R and TE? Well, it's a surface of revolution because it has symmetry of translations in TE. So it's relatively easy to draw. It's sort of like what you might call a semi-infinite cigar. It has this rotational symmetry. So r equals 2 gm. The horizon is the tip of the cigar at r equals 2 gm. R is infinity out here. And TE is the angular variable. And the fixed point set are on one side, where TE is 0. But then it goes back down on the other side, where TE is 4 pi gm. So the fixed point set is actually a manifold, but it's not just TE equals 0. Notice that if you only took into account the fixed point at TE equals 0, the fixed point set would not be a manifold. It would end at the horizon. But the fixed point set of a symmetry of a manifold is always a submanifold, not a submanifold with boundary. So that can't be the right answer, and the right answer is that the fixed point set continues on the other side at T equals 4 pi gm. Of course, what's going on in part is that T is a bad coordinate at the horizon. So along the fixed point set, it's discontinuous and jumps from 0 to 4 pi gm. So now by the bottom half, I just mean literally the bottom half in this picture. And as I told you, this picture is easier to draw than the corresponding, Since I'm only going to have to draw pictures inside a two-manifold, which is this surface of revolution, the pictures are easier to draw than they were yesterday with de Sitter space. That might have made the de Sitter lecture harder to understand. So we define this state psi prime of W by saying that, so the fixed point set, I'll call S. So the picture is getting a little busy here, but S is this fixed point set, both parts on both sides, at either T equals 0 or T equals 4 gm. And so I define the state psi W. W is the lower half. So, well, S divides the two-manifold into two halves. W could be either one, but in the picture I'll take the lower half, as we took the lower hemisphere yesterday. Then the state psi W is defined in the usual way by a path integral over all fields on W, such that phi W on S is phi S. And we have the exponential of minus the action. As far as I know, it works. It's working. Okay. So this was unnormalized. Again, we define a normalized one by dividing by the square root of z. So this has the property that it is a quantum state. On the other hand, it's not obviously invariant under rotations of the surface. In other words, it's not obviously invariant under translations of TE because it was defined as the integral over half of the space with boundaries at T equals 0 and 4 pi gm, which aren't invariant under rotations. So we're in the same basic situation we were yesterday. We had a formula for correlators and we had a definition of a state. And one has the symmetries and the other is a quantum state, so we want to know they're the same. And the proof is the same as it was yesterday. Well, the proof, we want to know that this is true for arbitrary correlators. Well, we first consider the case that the correlators are all inserted on the surface S. I called it that kind of S. Then if the operators are all inserted on the surface S, it's, the argument I gave yesterday was as follows. If we're working in the state psi prime W, how would we calculate this? Well, we create the ket, I guess, by an integral in the lower half of Euclidean Schwarzschild. Then we create the bra by an integral in the upper half. If we just wanted the normalization of the state psi prime w, we would just glue the top and bottom together. But to calculate a path integral with operator insertions, we simply insert the operators on the points P1 up to PS before the gluing. And so therefore this is simply given by a path integral on the Euclidean Schwarzschild spacetime with those operator insertions. And okay, by definition, that's equal to what we're calling psi HHI or psi prime HHI with these insertions. So that's if the points are inserted on the midplane. But then if we differentiate with respect to their positions any number of times, we're still looking at correlations of local operators inserted on the midplane, so the same logic applies. And then we claim that the Taylor series converge as long as we're not running into singularities, which we won't in Euclidean signature. Yes? The question is what we say about how we define the path integral on this surface given that it's not compact. Well, you do whatever you did when you learned about quantum statistical mechanics on R3. So when you study thermal correlations on R3 times a circle, well, naively you take the fields to approach their expectation values at infinity. Their expectation values in a thermal ensemble. But anyway, near infinity, we just have an ordinary R3 times a circle, so you do whatever you would have done there. Any other questions? So, hopefully we've convinced ourselves that the normalized Hartle-Hawking-Israel state, which is the one whose expectation values are the Euclidean Schwarzschild correlation functions, is a quantum state because of this relation. In other words, well, we've constructed a quantum state that also has the Euclidean Schwarzschild correlators as its correlation functions. So what are we going to do with it? Well, in a moment we'll continue to Lorentz signature, but let's discuss what we can see in Euclidean signature. W was this bottom half of the cigar. So W near R equals infinity was just R3 times an interval whose thickness was beta Hawking over 2, 4 pi gm, not 8 pi gm. So psi w near infinity is a normalization factor times e to the minus 4 pi gm times the Hamiltonian, where h is the Minkowski space Hamiltonian. In Rindler space and the de Sitter space, I had to tell you what operator we were treating as the Hamiltonian, but here it is literally the usual Minkowski space Hamiltonian. So I hope you all recall that this is, therefore, the thermofield double state of a thermal ensemble in Minkowski space. It's not e to the minus beta h, it's e to the minus beta over 2 times h. So the density matrix would be e to the minus beta h. The thermofield double state is the square root of the density matrix, so it's e to the minus beta over 2 times h. And here we're getting the square root of the density matrix, because to get the density matrix, we'd have to go all the way around the circle, but here we've only gone halfway around. So near infinity, it's obvious that this is the thermophile double state of the radiation, the black body radiation near infinity. But what I want to claim is that it's actually the thermophile double state of the whole system, including the black hole. And the steps for proving that are going to be exactly the same as they were for both Rindler space and de Sitter space. The only thing which isn't clear to me is whether I want to explain that before or after continuing back to Lorentz signature. I think I'll explain it before. So, we've constructed this state on the hypersurface S, which is the boundary of half of Euclidean Schwarzschild space. Remember, all my pictures are multiplied by a 2-sphere, or in d dimensions, a d minus 2 sphere, which I'm not drawing. Mercifully, since that factor is factored out, I can draw 2-dimensional pictures, which are easier to explain. Now, S has a sort of midpoint on the horizon, and the horizon divides S into what I'll call SL and SR, the left and right parts of the horizon. Now, now we're going to proceed as we did for both Rindler space and de Sitter space, but I perhaps rushed it too much for de Sitter space. H is the space of Hilbert space of functions of a field phi s. Phi s is a field on S. But I'll split phi s as a pair, phi on SL or phi on SR. Maybe I'll just call it phi L and phi R. So correspondingly, I formally split H as HL tensor HR. So the state that we constructed, psi W, is in H, which is HL tensor HR. Okay. What we want to construct is a density matrix. I'll let rho L and rho R be density matrices for observations in the state psi W only in SL or SR. So after we construct these density matrices, we'll continue to Lorentz signature and give a space-time interpretation. For now, we're going to give a Hamiltonian interpretation of these density matrices. So we imagine observations made only on one half or another of this surface, and we want to construct the density matrix appropriate for those observations. So for example, what is rho R? Well, to construct rho R, we take the trace over H left of the pure state density matrix of the state W. That's the definition. So it's 1 over Z times the trace over H left of the pure state density matrix of the unnormalized state. And apart from the factor of 1 over Z, the unnormalized state is given by a path integral on the lower half of the Euclidean Schwarzschild space. As I hope you're getting tired of hearing me say, this is the ket, and the corresponding bra is a path integral in the upper half. Then how do we construct the density matrix? Well, we do what we always do. So we have 1 over z times the trace over h left of psi prime w of phi left and phi right times the corresponding bra, I guess, phi left prime and phi right prime. To take the trace means we set phi left equals phi left prime and integrate. In terms of path integrals, that means we glue together this half with this half. And after gluing them together, we have a path integral on the whole Euclidean Schwarzschild space, just with a cut at t e equals 0. No cut at t e equals 4 pi. So, sorry. I'm a little bit worried that my claim I can draw convincing pictures is going to prove to be an exaggeration. Okay, what I've tried to draw is the semi-infinite cigar, and then somebody's taken a knife and cut it, starting at the horizon and going off to infinity, but not with no cut on the back side, only a cut on the front side. Well, how would you build up that path integral? Or maybe I should say, how would you represent what that path integral is doing by an operator? Because after all, the density matrix is naturally seen as an operator. The answer you're supposed to give me is that we take the region S right, the region where the cut is, and we rotate it by an angle 2 pi inside the Euclidean Schwarzschild black hole. So what we're supposed to do is what we always do. We have the Hamiltonian. The Hamiltonian is an integral over the initial value surface S. I'm not sure whether to call this S times S2 or to understand that S really includes the S2. S is the initial value surface, which includes the one manifold I'm drawing and the hidden 2 sphere. So let's say that S includes the S2, or SD minus 2 in D dimensions. The Hamiltonian is, well, roughly, I haven't written it in a good generally covariant notation, but it's roughly the integral of T00 over the initial value surface. Let's settle for that. But then, as usual, we write the Hamiltonian as HR minus HL, where HR and HL are integrals over the right or left region. The reason for including the minus sign in the definition of HL is that, well, in Euclidean space, if I rotate the picture, the front side goes upward, but the back side goes downward. And if you want to define HR and HL to map them both forwards, you need to include a minus sign in one of the definitions. And then the formula for H is HR minus HL. If you don't want, well, sorry. I think I'm paying a price for the fact that I was too casual in the way I defined H. I should have written H. Let's go back here. I should have defined H as an integral over S, d sigma mu, of T mu nu times the killing vector field V nu. Then you'd see the sign, because the killing vector field moves upwards here, but on the far side it moves downwards. So the killing vector field is odd under the exchange of the two sides. And if you want to define HR and HL to be symmetrical under that exchange, you need a minus sign in HL. You don't have to do that, but it's traditional to define things with the signs I've done. So now that we know what HR is the operator that generates a rotation just on half of the initial value surface. Now you can hopefully see from this picture is meant to show us, remember this picture is the one that computes rho r. Rho r is computed by a path integral on that picture. So rho r of phi r and phi r prime is given by a path integral on the cigar with a cut on the positive part of the surface S, and with boundary values phi r and phi r prime above and below the cut. So to construct that as an operator, we do the same thing we did in Rindler space and the same thing I tried to say in de Sitter space yesterday. We start with a state on SR, on half of the hypersurface, and we rotate it in Euclidean space by an angle 2 pi. So what we're supposed to learn from that then is that rho r is e to the minus beta Hawking times hr, except divided by this normalization factor. So that's a thermal density matrix in the region SR with HR as Hamiltonian and temperature, the Hawking temperature. Well, is it sensible to call HR the Hamiltonian? If you're far away from the black hole, HR is the standard Hamiltonian, so it must be sensible. Of course, the same logic would apply to rho L. Rho L is likewise thermal at the same temperature with now Hamiltonian HL. And we could ask about the thermophile double state. Oh, sorry. I will stop here, though, for a second. Any questions?
I may be struggling to formulate my question all the way in the back. So in the case of Rindler space, we knew that the left and the right Rindler wedges don't talk to each other, and they meet at the origin.
We'll see the analog. We haven't gotten back to Lorentz signature.
Okay.
If you want to ask such a question, ask it again in about 5 or 10 minutes.
Okay.
Any questions on the Euclidean space picture? Okay, well now we'd like to understand the thermophile double state. And the thermophile double state as an operator is just the square root of the density matrix. So it's 1 over the square root of z times e to the minus 1/2 beta h times h right. I just took the square root of the formula for the density matrix. Since we got the density matrix by rotating the positive region SR through an angle 2 pi, the square root rotates it through an angle pi. But if we rotate through an angle pi, if you start with this positive half and rotate through an angle pi, what we build up is just the lower half that we call W. So therefore, since the path integral on W by definition is the state psi W, which we also decided was the Hartle-Hawking Israel state, we learned that the thermophile double state, rho r to the 1/2, is just the Hartle-Hawking Israel state. So these are the two main conclusions we had for both. So two main conclusions. So, well, okay. Two main conclusions are that the Hartle-Hawking Israel state is thermal. Sorry. The density matrix on the right-hand side is thermal density matrix. And the Hartle-Hawking Israel state is the thermophile double state. So if you view the left and right-hand sides as thermal systems at the Hawking temperature, then the thermophile double state is just this Hartle-Hawking Israel state. So I think we're finished with the Euclidean picture, and the next will be to rotate to Lorentz signature. So maybe I'll ask for any questions here again. Okay. Well, remember we defined the surface S as the fixed point set of a symmetry TE going to minus TE. And now we can rotate back to Lorentz signature. And remember, when we rotated from Lorentz signature to Euclidean signature, we used the fact that there was a symmetry T to minus T. And if we take the fixed point set of that symmetry and proceed from there in the imaginary direction, that automatically gives us a real metric. That was because, well, Gij of T was Gij of minus T because of the symmetry. And then because the metric is real, that was the same as Gij bar of minus T. And this being equal to this tells us that Gij bar of TE is Gij bar of TE. Oh, sorry, I need a bar. So I didn't explain it very well here. But the existence of the symmetry under T going to minus T meant we could continue to Euclidean signature from Lorentz signature. Now we're in the same situation in reverse. We have a symmetry TE going to minus TE, so we can continue to Lorentz signature. So our surface S was defined as the fixed point set of this symmetry. So if I transform TE back to I times T, I think I usually have a minus sign here, then automatically S will be real in Lorentz signature. But now we're going to run into something which is a most remarkable phenomenon. But I have no idea, I suspect a lot of you have seen it before, not in reference to black hole thermodynamics. As I told you, I myself learned about this as a student long before I seriously studied black hole thermodynamics. So if you look at the Euclidean space picture, you see there's the outside the horizon region, SR, which is really where we started. It's the region where TE was 0. So that was the naive continuation of T equals 0 from Lorentz signature. But to make this construction in Euclidean signature, the initial value surface we had to use had a far side as well. The left-hand side at TE equals 4 pi GM. And that was a bonus in this construction. And that bonus is going to still be there when we go to Lorentz signature. So therefore, what's going to happen in Lorentz signature is that we're going to get a two-sided picture with the outside the horizon region we started with and a second outside the horizon region on the other side, one corresponding in Euclidean signature to T equals 0 and the other corresponding to 4 pi GM. Now, the most efficient way to see that picture is to use the Kruskal-Szekeres coordinates, which we actually briefly used on Wednesday, I guess, for a technical purpose. We were just trying to describe the outgoing null geodesics. But here, we're going to use them for their most important application, which is to describe the continuation of the short shell geometry outside the horizon, or beyond the horizon. As I've said a few times, I have no idea to what extent you've all seen this before. So naively, we just change coordinates from R and T to capital U and capital V. And then if you want to know, you could find an elementary formula I won't write for T, you'd find the exponential of t is something like v over u. But there's no simple inversion for r. If you want to know what is r, you have to define r implicitly by this formula here, which we get by multiplying those two equations. But this function here is a monotonic function of r, going from 0 at the horizon, r equals 2gm, to infinity when r is infinity. So, let's see, what am I trying to say? Well, I don't remember what I said exactly. But anyway, the function of r on the right-hand side is monotonic. So in terms of these coordinates, the metric takes a simple form, which I actually also wrote the other day. What's important about this is that as long as r is greater than 0, this is all perfectly good. If r is 0, then uv is 1. So you find that as long as uv is bigger than 1, the metric is smooth. So in this form, we can continue past the horizon. Nothing bad happens at r equals 2gm in this way of writing the metric. R equals 2gm just means that the product uv is 0, so one of them will be 0. But nothing goes wrong with this metric if either u or v or both are 0. The only constraint is that we have a 1 over r, so when r goes to 0, there's a potential singularity, and if you calculate the curvature tensor, you'll discover that r equals 0 is a true singularity that you can't avoid. Curvature invariants like the square of the Riemann tensor blow up at r equals 0. So the spacetime really does end at r equals 0, which means it ends at uv equals 1. But there's no other condition. So the full spacetime picture is as follows. First of all, as one person asked me the other day, u and v are null coordinates, so I'll draw them as such. When I say that u and v are null coordinates, I mean that keeping the angles on the two-sphere fixed. If you change u or v, keeping the other one fixed, that's a null direction. And therefore, I should draw it as being at a pi over 4 angle from the vertical. So I've drawn the u and v axes at pi over 4 angles from the vertical. And then uv equals 1 is this hyperboloid. And uv equals 1 is a two-sided hyperboloid. U and v could be either both positive or both negative. And so the space-time ends when uv is 1. But it's got two asymptotically flat regions. You see, if I go to the left or right in the picture, either u is positive and v is negative, or vice versa, so the product uv is negative. And this nice formula shows me that if uv becomes very negative, then r becomes large. So when uv is going to minus infinity, r is going to plus infinity. So that's the asymptotically flat region. So in learning to continue beyond the horizon, we got a bonus. We studied the black hole for a long time from the perspective of an observer outside the horizon, but then we continued the Schwarzschild geometry past the horizon, and we found that there's another asymptotically flat region on the other side. I should stress that this is for the ideal Schwarzschild solution. In the first lecture and also the beginning on Wednesday, we studied a more realistic case in the real world of a black hole that forms by collapse of a star. In that case, the Schwarzschild solution was only valid outside the star, and hence we did not have this full picture. Today we're discussing the idealized mathematics of the full Schwarzschild spacetime, and it turns out to have this amazing picture with a continuation beyond the horizon. So there are two asymptotically flat regions, UL and UR. So UL and UR are the domains of dependence of the partial Cauchy surfaces that I called SL and SR. So, okay. What I called the fixed point set of TE going to minus TE. Well, the symmetry TE going to minus TE in these coordinates, oh, I hope I've got it written down. It's something like I think it's U going to minus V. But in any case, it's whatever the formula is, the fixed point set is that horizontal line in the picture. And what previously were SR and SL are simply initial value surfaces at time zero. Well, one of them is the initial value surface at time zero in the region we started with outside the horizon, which I'm now drawing on the right. But in Euclidean space, we have that bonus, the second half of the initial value surface, and that appears over here as S left. And you can see that the outside the horizon regions that I've called U left and U right are now the domains of dependence of S left and S right. So we can reinterpret what I called rho L and rho R are the density matrices for UL and UR. So in particular, we learned that physics for an observer in either UL or UR is thermal, with HL or HR as the Hamiltonian and at the Hawking temperature. I remind you that the observer who remains forever in UL, for example, or UR, unlike the Rindler observer, doesn't have to accelerate. You could be orbiting the black hole forever in a stable orbit, and you'd experience this thermal physics at the Hawking temperature. Now, I hope this picture reminds you of the picture we had for Rindler space and also the picture I tried to draw but perhaps rushed too much for de Sitter space. To make the picture fully clear, what I should add to it is the action of the Hamiltonian. The Hamiltonian is d by dt in Schwarzschild coordinates. So if you want to know what it does in terms of U and V, you should look back here. And you'll see that up to a factor of 1 over 4 GM, the Hamiltonian is 1 over 4 GM times V d by dV minus U d by du. The picture is becoming very busy, so I want to start again. So you've seen this picture before when we were discussing Rindler space, except that we didn't have the cutoff at UV equals 1. So the metric on this picture is different from what it was when we were doing Rindler space, but the picture is the same. And we have UR and UL, which correspond to what I think I called RR and RL, the Rindler regions. Now we have these asymptotically flat regions outside the horizon on one side or the other. And we have the Hamiltonian which is 1 over 4 gm times v dv minus u du. So apart from the 1 over 4 gm, that's a boost generator. So it acts like I keep drawing. I hope you've seen these arrows before. The arrows indicate that H moves us forward in time on the right, backward in time on the left, and is space-like in the future and past wedges. So the reason for the analogy we found between Rindler space, de Sitter space, and the black hole, well, in the case of the black hole, the symmetry of time translations at infinity looks like a Lorentz boost near the horizon. That's what we've learned by learning how to continue the geometry past the horizon and by picking good coordinates u and v near the horizon. The same thing is true in de Sitter space, except that in de Sitter space you have to talk about the past and future horizons of the observer. And then by H, you mean, well, first you picked an observer. The choice of an observer in de Sitter space picked us a particular H that moves that observer world line forward in time. And that H near the observer past and future horizons looks like a Lorentz boost generator. I attempted to explain that yesterday, but perhaps rushed too much. So the fact that the important symmetry is a boost generator near the horizon is the reason for the analogy between Rindler space, de Sitter space, and the black hole. In Rindler space, we got that for free because, to begin with, we were talking about the Rindler regions, and the only symmetry was the boost. Well, we could have worried about the normal directions, but the only symmetry acting on the two directions in the picture was the boost. So in Rindler space, we started with the boost, just as we started with the vacuum state. In the other cases, we had to do some work to construct the appropriate state and understand its properties, and it also takes some discussion to explain that what is the important symmetry and why, in what sense it's similar to a boost. But the reason for the analogy, Rindler, de Sitter, black hole, is that in all three cases, the important symmetry is the boost. I wonder if I'm finished with the black hole, or what else am I supposed to say? No, okay. I'm finished, except that I'll draw the, yeah, okay. I'll draw up a couple more pictures, but we're basically finished. Any questions? Oh, well, okay. If there aren't any more questions, then all I'm going to do with the black hole that remains is to draw Penrose diagrams. So this picture I've drawn is very illuminating, but it's not a Penrose diagram in the usual sense because u and v go off to infinity. So to make a Penrose diagram, you just reparameterize u and v, replacing them by functions of themselves that have finite ranges. So you replace u with something like, I don't know. I don't remember what's a convenient function, but an example of a function that would do would be to replace u and v by tanh u and tanh v, which run over finite ranges. And then, if you use those coordinates, the Penrose diagram looks like this. So, here's the singularity at r equals 1. Oh, I remember what I haven't said about this picture. Well, I'll do more than just draw pictures. Then here we have future null infinity. Past null infinity. Here we have the region I called u right, here's u left. And we have also here future null infinity. And here we have past null infinity. Okay, so that's what the Penrose diagram looks like. It's the same picture I had before, except reparameterizing u and v so that we can see infinity at a finite distance. So I should maybe stress u is infinity here. V is infinity here. U is minus infinity here. U is infinity here, and V is minus infinity here. We've just reparameterized to put U and infinity at finite distances so we can see the whole picture. Now, something you'll see about this picture is that an observer in U left or an observer in U right cannot communicate with each other. The space-time is connected, but they cannot communicate, because if you send a signal from U left, for example, it'll travel at most at a pi/4 angle from the vertical, so, well, it could escape to infinity, or it could end up at the singularity, but any signal emitted from here will end in somewhere in this region, and will never reach U right. So, if you like, in space, there's a wormhole that connects U left and U right. Actually, I'm going to, I do have more to say about this picture than I remembered, and so we'll go on more than I thought for the buckle. I'll draw a picture of a wormhole in a bit. But because the geometry is connected, spatially, U left and U right are connected. But causally, they're not. You can't communicate from U left to U right, nor can you communicate from U right to U left. A signal emitted here will end up somewhere in that region. Now, that's the geometry, but what about the quantum mechanics? The quantum mechanics is that the state, psi TFD, is an entangled state of UL and UR, and it's in fact the thermofield double state. So it's just 1 over the square root of Z times the sum over energy eigenstates I is the ith eigenstate of the operator H right or H left. In the thermofield double state, you consider pairs of states right and left that have the same energy, so it doesn't matter whether we consider here H left or H right. The thermofield double state is this highly entangled state between the two observers on the left and right. So in quantum mechanics, they share this highly entangled state. Now, this type of relationship between two systems has been considered enigmatic since early days of quantum mechanics. But whatever you want to say about it, it does not enable communication. So if you and I, in different laboratories, share an entangled state, my electron is entangled with your electron, let's say in a state of spin 0, that does not enable us to communicate. So, in general, we have two quantum systems A and B, and we have a state psi AB in HA tensor HB. And there are corresponding density matrices. Everything I can do, assuming I'm in lab A, is to make measurements in row A. Everything you can do is to make measurements in row B. If I manipulate the state, so if A manipulates the state, A can operate by psi AB going to UA tensor 1 on psi AB. In other words, you can apply a unitary operator on system A, but you can't act directly on system B. That will transform row A to UA, row A, UA inverse, but it will do nothing to row B. So whatever observer A does to the system does not change the density matrix of system B, and therefore does not affect any measurement made by the observer who has access to system B. That's the general relationship in quantum mechanics when you have an entangled state of two subsystems. It's a subtle correlation function which can be used to violate Bell's inequalities, but it can't be used for communication. So the geometry, in an uncanny way, realizes the same thing. In some sense, the worlds of observer on the left and observer on the right are connected, but they're not connected in a way that would let these observers communicate, because they're at space-like separation. So in the geometry, they're at space-like separation. In the quantum mechanics, they share an entangled state, but that doesn't provide a way to communicate. I guess the last thing I'm going to say about this is to try to give you another picture of the wormhole. So I'll take the surface S. So I'm going to, let me see. The way I described S so far was I said, let's forget about the two-sphere. Let's just look at the cigar. And then S in the cigar is just a line. That was okay for everything I've said until this point. But if you want to know what S really looks like as a three-manifold, that's not a very good picture. I'm now going to draw a picture where we remember the three-sphere. So the important thing is that the radius of S2, which is R is infinity here, and R is also infinity on the backside. It goes to a minimum 2 GM at the horizon. So the two-sphere out here is very big. It shrinks, and then it becomes big again. So I'm going to draw a picture of a three-manifold. Well, I'll draw a two-manifold. I can't really draw a three-manifold on the slide. So I'm going to represent the two-sphere as if it was a circle. So near R equals infinity, I have a plane, which I want you to imagine drawing circles in this plane. And those circles are supposed to represent the two-sphere. And the distance from the center is this function R. So R equals infinity out here. But when you get into the origin, okay, at infinity it's flat. But then when you come inward, the size approaches a constant. And then it blows up again, which I'll draw by drawing another sheet, where R is infinity out here. So this is another picture where I'm showing S right. What did I do? I might need to be rescued. It's okay if we have to open a new window, a new notebook, because it doesn't matter. A new notebook is fine. I'll just draw the picture again. And we don't need previous ones. Oh, thank you. Okay. So the picture was two worlds connected by a wormhole. The wormhole is sometimes called an Einstein-Rosen bridge. I've never read this paper, but I guess Einstein and Rosen had the three geometry at t equals 0 with the continuation past the horizon, but they didn't have the full four geometry, as later discovered by a variety of authors, but in the most useful form by Kruskal and Zagaris. So, at time 0, there's a wormhole connecting two asymptotically flat regions of space. But woe be unto you if you try to go through the wormhole, because you will end up at the black hole singularity. That's what we learned from here. Well, we learned from somewhere. Okay, well, yeah, we learned from here. If you try to go, if you start out here and think we've got this nice wormhole, so let's go there. But since you can't travel at more than a pi/4 angle from the vertical, if you go past R equals 2 GM, you'll end up at the singularity. I think that's all I want to say about the asymptotically flat black hole. I want to say just a word about the case of negative cosmological constant. First, there's the ADS Schwarzschild solution that I actually wrote yesterday. But you can do, everything I've said can be repeated for that case. A difference is that when I draw this 2 manifold that was parameterized by R and TE, it doesn't have a fixed circumference at infinity. Its circumference blows up at infinity. But otherwise, all my pictures would be the same. So everything is the same, except the final Penrose diagram looks different. The final Penrose diagram looks like this. The lines I've drawn are meant to be at pi/4 angles from the vertical. There are the 2 entangled regions, UR and UL, but their boundaries are time-like instead of being null boundaries. So remember, the Minkowski space version of this picture had null boundaries. Which means that in Minkowski space, null rays can go out and explore those wide open spaces at infinity. But in anti-de Sitter space, a massive or massless particle that goes off to infinity is actually reflected back in a way I explained heuristically yesterday. It's reflected back because from a bulk observer's point of view, it becomes very cold near infinity. So whatever energy you have is too high, and you're reflected back. Anyway, you could find that out by, solving geodesic equations or whatever. There's some subtleties, but the answer is that you get reflected back. So the picture in anti-de Sitter space is that there are time-like boundaries where the dual conformal field theory lives. So the continuation of the Adia-Schwarzschild spacetime beyond the horizon, again, is two-sided. But now the two sides can't communicate, and quantum mechanically they're entangled in the thermofield double state. Or more precisely, quantum mechanically there is an ideal thermofield double state in which they could be entangled. And that's the one that's naturally produced by a path integral in Euclidean signature. But the only difference is that now the thermofield double state in ADS-CFT duality, this state psi HHI is the thermofield double state of a pair of CFTs entangled at the Hawking temperature. So everything for negative cosmological constant is the same as I've said with positive cosmological constant, with zero cosmological constant, except that there's an additional interpretation in terms of the dual conformal field theory. And since this additional interpretation manifestly makes sense, not being limited to perturbation theory in G or anything, it tells us that the bulk description also makes sense beyond perturbation theory. Okay, this is a good time for questions. I think I really have said what I wanted to say on the black hole. Yes?
Yeah, I'm here. So it's maybe a bit naive question from my side. So given that, let's imagine that we have a pair production near the horizon, and let's say for local observers, so all quantum numbers are conserved. Let's say a lepton number or whatever. But for remote observers, so we will see only like a single particle, right, from the Hawking radiation in this case, or do I misunderstand?
I'm not sure I understand the question.
So the question, so let's say we have a pair production near the horizon.
Yes.
And so for local observers, so we see like two entangled particles, and so the quantum numbers are conserved, let's say like a lepton number. Yeah, but what is the picture for a remote observer? So do we detect on
the picture for the remote observer is what I explained Tuesday night. The remote observer sees thermal radiation going out, and if there is a global charge, there will be fluctuations in the outgoing radiation, because after all, in a thermal ensemble, there are fluctuations in the charge. Your question is really a question on the first lecture Tuesday, or which I reviewed Wednesday, but the answer is certainly that you'll see whatever fluctuations are expected in thermal radiation. Any questions, other questions on today's lecture?
Is there a difference between the pair of CFTs entangled for small ADS black holes and large ADS black holes?
Well, there is a difference, but to explain it properly really takes a different lecture from what I've given. I'll say a couple words, but you might not fully understand it. If you have any thermal system, you can define what's called the thermofield double Hilbert space. Oh, sorry. But the thermofield double Hilbert space may or may not be simply a tensor product of two copies of the original Hilbert space. So here at low temperatures, everything I said is true regardless, but it's more interesting when the thermofield double Hilbert space is not a simple tensor product of Hilbert spaces. And that will be the case. That will be the case when the black hole is stable. The full phase diagram of this thing is more complicated than I explained, because there can be in ADS5 times S5, there can be black holes that are localized on the S5. So the full story is actually rather complicated. If I try to make complete statements, I'll get them wrong, and anyway, they're model dependent. So let me stop here where what I've said is more or less correct.
In the case of ADS Schwarzschild black hole, in
Yes.
case the black hole is the result of star collapsing in ADS, can we still construct the thermofield double state?
Well, first of all, we can construct the thermofield double state regardless of whether it describes the physics you're interested in. So when you talk about a star collapsing, that wasn't the thermofield double state, that was some other state you were interested in. So we can discuss that state. I think, let me try to give an interpretation of your question. Your question might be, if we consider a state which is initialized with a star in ADS that collapsed to a black hole, is it somehow related to what we've discussed?
Yeah, because we made the comment in asymptotically flat space that we don't have the two, we don't have the same diagram, right? If
Yes,
the black hole is exactly right.
Well, I think if we discussed it in ADS, there are extraneous issues. So let's discuss this in an asymptotically flat space. So I'm going to interpret your question to be the following. In the real world, consider a black hole that, consider a star that collapses to a black hole. Is the resulting physics related to the thermofield double state that we've described?
Yes.
Okay. Well, you see, why is statistical mechanics correct? Statistical mechanics is correct because for a complex system, a generic state is indistinguishable from a thermal state with the same values of the thermodynamic observables. So even if a state, take a cup of tea. If you want to know whether it's described by a truly thermal density matrix, knowing that would depend on a knowledge of its history. And you will usually have trouble arguing that your cup of tea is truly described by a thermal density matrix. But when you study statistical mechanics, what you learned was that a generic state for all practical purposes is indistinguishable from a thermal density matrix. That's why we study thermal density matrices, not because we think that in the real world everything we run into is truly described by a thermal density matrix, but because we've convinced ourselves that a generic state is all but indistinguishable from a thermal density matrix. All but indistinguishable means that if you have a state made from n atoms, it might take a joint measurement on a large fraction of all the atoms to distinguish the actual state you have from an ideal thermal equilibrium. So this is the situation in statistical mechanics in general, and is the reason we study thermal density matrices, even though normally the systems we encounter in nature are not literally in a thermal density matrix, or at least we don't know if they are. In fact, since it's impractical to distinguish a generic state from a thermal density matrix, normally we literally don't know if we have a thermal density matrix, but we say we might as well assume we have one. Now, black hole thermodynamics says that a black hole is no different from a cup of tea for issues like that. So after the star has collapsed to a black hole, it's going to be all but indistinguishable from a black hole described by a thermal density matrix. Is that satisfactory for answering your question?
Yes, thanks.
Okay, sure. I thought that was better than taking the question literally in anti-de Sitter space, which would have involved some extraneous issues.
Sorry?
Yes?
You used de Sitter as an analogy. I was wondering, could you comment on black holes in de Sitter?
Well, there is a Schwarzschild de Sitter solution, but it is a little bit more complicated to study because there are both black hole and cosmological horizons, and they're at different temperatures. So there is not a state as nice as this state I called psi ds for de Sitter without the black hole, or what I called today the Hartle-Hawking Israel state for the black hole. There is an Unruh state. So if I were lecturing about Unruh states, I could have more easily described that example.
So about the argument that you made, why there is a reflection in anti-de Sitter and that it relates to a cold temperature.
Yes.
I'm not sure I understand why the cold temperature reflects. Is it because of Kirchhoff's law of radiation that if you have zero temperature, you don't emit?
No, well.
You don't absorb, so you
See,
reflect.
it might have been better to say that there's a G00 blows up at infinity. So your effective energy goes to infinity. Instead of saying the temperature goes to zero compared to your energy, which is the way I described it, I should have said perhaps that your effective energy goes up, or sorry, it would have to go up. To penetrate, okay. If you study a wave equation in anti-de Sitter space, you'll discover a reflection from the boundary. There are a few tricks involved in that statement. You need to understand what kind of boundary conditions are sensible in anti-de Sitter space. So if you learn about the ADS-CFT correspondence, this is one of the first things you'll learn about. Because of the fact that many of you have already learned about it, and because of the fact that the details aren't going to help us with understanding black holes and black hole thermodynamics, I didn't want to really explain it, so I kind of cheated yesterday, and it might have been less than convincing. But it is true that particles or waves in anti-de Sitter space effectively get reflected from the conformal boundary. Any other questions? Yes?
Yeah, I have a question about the anti-de Sitter black holes from yesterday.
Yes?
You said when beta is low enough, there are two black holes that are stable thermodynamically.
No, only one stable.
Yeah, but
there are two solutions,
right,
of which one is stable.
And one is stable because the action is lower. But
No. Sorry.
I thought they were both thermodynamically
Well,
stable.
for the black holes, one is always locally unstable. When beta is low enough, in other words, when the temperature is high enough so that there are two black hole solutions, the small black hole is always locally unstable, just as the black hole in Minkowski space.
All right.
When I had two things that were locally stable, they were the big black hole and the gas of thermal radiation.
Right, so my question was about that. Sorry,
Yes.
I got confused. And the reason one is stable more than the other is because the action is lower for
Yes.
the other one. But
And we can be more precise. The gas of radiation has zero action, so it's just a question of whether the other one has positive or negative action.
right. But is unstable compared to what? Because these are solutions, are entire histories, right? They're like
Well,
entire universes.
think of them as states of the universe.
So it would be like a quantum transition.
Well, it would be like, well, it's a first order phase transition. So if you have a glass of water and you heat it at a certain temperature, it will freeze. But it won't freeze instantly when you cross the transition temperature because it's a first order transition with a jump in state, not a continuous transition. So in that example, what will happen is that a small nucleus of ice will form and then it will grow. Now, as I said yesterday, a mechanism for the transition in this case isn't really understood. But thermodynamically, it's like a system with two states, water and ice, at one range of temperatures. One has lower free energy. At the other range, the other has lower free energy. So we expect that there will be a transition from the higher one to the lower one, depending on the temperature.
And the expectation is that this will happen, like, it will start locally somewhere because somehow the vacuum knows that it's in the wrong state. Or
That's a reasonable guess, but nobody has, to my knowledge, nobody has said anything useful about this transition.
all right, thank you so much.
Here, I have a question. So during the derivation of the black hole, we use the short-tail metric, which is time symmetric. But how would one proceed, for example, in the Kerr metric, where we have these cross terms?
Well, we can't study the Kerr case in exactly the same way I've described, because first of all, it doesn't have an equilibrium state like the Hartle-Hawking Israel state. It does have an Unruh state. So, as I said in answering the question about Schwarzschild de Sitter a moment ago, there are these cases where we should be discussing Unruh states, which I'm not going to be talking about. Also, it doesn't exactly have a Euclidean metric. It has what Gibbons and Hawking called a quasi-Euclidean metric. You have to use a complex metric, and you get what appear to be sensible answers by Euclidean thermodynamics, except using a certain complex metric for the Kerr case. It's a complex metric with what seems to be nice properties, but the fundamentals aren't clear. Well, frankly, even when we can use real metrics, the fundamentals of Euclidean black hole thermodynamics aren't terribly clear, and certainly they're not clearer in the Kerr case. But that's what's been done. The only trouble is that, well, we're not going to head there today.
Okay,
but you can read about it.
Thanks. So I've got a question about ADS black holes.
Mm-hmm.
So if I'm an observer outside of the black hole and see some kind of thermal density matrix, at least in this what we discussed, this ideal case, it seems like the thermal field double state has a very intuitive geometric interpretation in terms of some other half on the other side of the black hole connected to some wormhole that I'm kind of tracing out of. So if I have some generic black hole which formed through collapse or something like that, which is one-sided, is there also some intuitive interpretation of the thermal field double state or of some thermal field double state like that?
All I can tell you is that, as I discussed in a previous question, the logic of statistical mechanics tells us that what we get when a real star collapses to a black hole will be all but indistinguishable from the thermal field double state. But it's rather mysterious why the black hole in the real world is rather all but indistinguishable from one that does have this wormhole. That's not a question that anybody's going to be able to answer for you. The purpose of my lectures is to introduce you to some of the mysteries, and I warn you again that even with 7 lectures, I'm only scratching the surface. I see a question back there.
So in the end, you were talking about the ADS picture, and you came up with a pair of CFTs. So can we use those pair of CFTs to generate a Yangian? And will that, what will be the, if yes, then what will be the relation between the Yangian and the thermofield double and corresponding density matrix?
Well, I mean, Yangian is rather special to particular cases of integrable systems, which we don't necessarily have here. Maybe, do we really have more questions?
Yes, I have a question. I'm not so sure if I can follow the consequence that from what you mentioned that the Rindel picture and the de Sitter and the black hole picture have the same symmetry Dabus. So it tells us just that they are consistent with the same conserved quantity, or what else can we follow from that?
Well, the essential geometry was the same of all 3 cases. So, okay, thank you. So I can draw it again, but I hardly know what to tell you. Here was Rindler space. The black hole looks the same, except it's cut off. Part of it is missing, but the part we've got is the same, and it has a symmetry that looks the same. And then there was de Sitter. It's sort of cut off in a different way, but near the horizon it looks exactly the same. I tried to help you understand that there was a close analogy between the three cases. In Rindler space, we have the Rindler wedge and de Sitter space. I think I called the two static patches PR and PL. And in the black hole, I called the asymptotically flat regions UR and UL. But there was a close relation among all these three cases. And the essence of it is that near the horizon, the three pictures are exactly the same. What they're embedded in is different in the three cases. So the Rindler goes off to infinity, and the others are cut off in one way or another. And there's also ADS Schwarzschild, which is a variant of this. But near the horizon, it always looks the same. I had a dream to tell you a little bit about density matrices before lunch. Can we still do that, or do we have more questions? Yes?
Could any quantum effects like allow signals to traverse through the wormhole? Or would it be completely shut off by the topological censorship of classical geometry?
You see, we discovered here something very beautiful. Quantum mechanically, there's entanglement that is a correlation that doesn't enable communication. Then in gravity, we discovered the wormhole, which is a connection of some kind that didn't allow communication. I would assume that that's the correct answer because it's clearly the correct answer in the quantum mechanical case. So I would assume the answer to your question is no. We're not going to find a way to get through the wormhole. I might take advantage of a lull in the question to get started at least with density matrices. So the rest, okay. Well, okay. So I already in the first lecture defined the von Neumann entropy of a density matrix to be minus the trace of rho log rho. And then I said that the relation of the von Neumann entropy to a thermodynamic entropy is an inequality. And in the first lecture, I proved that in a microcanonical version. But instead of reminding you of, we're going to be making use of that, but I don't want to just remind you of it that way. So I decided instead I'd prove it in a canonical version. So in the canonical version, you ask the following. For all density matrices with the average value of the energy being E, the average value of the energy in a density matrix is the trace of rho times h. If I ask that the trace of rho times h should be some given constant E, what is the maximum that the von Neumann entropy can be? Well, this is a simple exercise with Lagrange multipliers. So the function we want to maximize is the trace of rho log rho. But we have a constraint that the trace of rho h should be E. And we also must not forget that density matrices are normalized. So we have another constraint that the trace of rho should be 1. So the normalized density matrix that has the maximum entropy for a given energy will be a stationary point of this equation, of that functional. And so varying with respect to rho, you learn that minus log rho plus lambda h plus lambda prime is 0. So you learn that rho is e to the minus lambda h times e to the minus lambda prime for some lambda and lambda prime. This is usually written e to the minus beta h over z. So you see, the density matrix that maximizes the von Neumann entropy for a given energy is a thermal density matrix with the temperature chosen so that the energy comes out correctly. And the temperature that will do that is unique because the heat capacity is positive. So there will be a unique temperature at which the energy is right, if there is one at all. Of course, you could specify an energy which is unachievable by the system you're talking about. But if the energy you asked for can be achieved by a thermal density matrix, there will be a unique temperature that does that. So this is a canonical version of the statement that the maximum of the von Neumann entropy is. Here we maximize the von Neumann entropy under a constraint on the macroscopic state of the system, which was the energy. There could have been more thermodynamic variables, charge and so on, and then a similar derivation with a Lagrange multiplier for the expectation value of the charge would have given a density matrix with a chemical potential. But anyway, this is the canonical version of what I said at the first lecture in an anti-canonical form, sorry, micro-canonical form. Now, for a complex system, something that's very important, which I actually said in answering one of the questions about 15 minutes ago, for a complex system, it's very hard to distinguish true thermal equilibrium in which the von Neumann entropy equals the thermodynamic entropy from any generic state. That statement is actually why statistical mechanics is useful. Normally we have a generic state which we don't know the details of, and the only reason statistical mechanics is useful is that the details of exactly what the state was don't matter, because we're usually not able to make the measurements that we needed to distinguish the state we actually have from true thermal equilibrium. Now, something else I also already, Then there's the important special case that we ran into in the thermofield doubles case. That's the bipartite system with the pure state of the combined system, as I explained in the first lecture. The generic canonical form of a pure system of a pure state of a bipartite system is not a tensor product, but a sum of tensor products where we can consider the states IA to be orthonormal and likewise IB. They're orthonormal states of the systems A and B. They may not be complete bases because there may not be enough of them, but we can assume they're orthonormal. Any bipartite state has a representation like this. And then the density matrices have the same eigenvalues. So they have the same von Neumann entropy. But more generally, they have the same measure for anything that only depends on the eigenvalues. So there's something called Rényi entropies, which are also important, and in fact we'll even use them in the lecture after lunch, I hope. The Rényi entropy of a density matrix of index alpha is this. it's useful because it's often easier to calculate than von Neumann entropy. But a little calculus will show you that the von Neumann entropy is the limit as alpha goes to 1 of the Rényi entropy. So often one understands the von Neumann entropy by first studying the Rényi entropy and then trying to take the limit as alpha goes to 1. And see, since rho A and rho B have the same eigenvalues, it follows that they have the same Rényi entropies. Now there's one more. Yes?
How do you define complex systems here on top? Just large number of interactions? Or?
The question is how you define complex systems. So if you ever studied statistical mechanics, what people told you was that for a sufficiently generic, okay, if you have a two-body system, you solve the equations of motion. If you have a three-body system, you're stuck. If you have an n-body system for a sufficiently large n and a sufficiently generic Hamiltonian, what they told you when you studied statistical mechanics was that there's a new simplification because any sufficiently generic state, any generic state, is indistinguishable from a thermal ensemble. So a complex system is a system that you can study with statistical mechanics. But it matches your notion of a complex system. When it becomes hopeless to study the equations of motion microscopically, that's when statistical mechanics is supposed to take over. I'm tempted really to go on for another 10 minutes on the grounds that you're not supposed to go to lunch before 1. So there's one more notion of entropy which is going to be important, and that's relative entropy. By the way, it would be even more important if I continued my lectures beyond today, but it'll still be useful today. So if rho and sigma are two density matrices on the same system, on the same system, what's called the relative entropy between them is given by this formula. And it's actually important, well, it has an interpretation in terms of how hard it is to distinguish rho from sigma by an experiment. If you think that, if your hypothesis is that a system is described by sigma, but the correct answer is rho, and you ask how hard it is by a measurement to learn that you were wrong, the bigger is the relative entropy, the easier it will be by an experiment to distinguish them, assuming the experiment is chosen correctly. But we're not going to need that. All we want to know is that, well, first of all, S of rho and sigma is 0 if rho equals sigma, and it's positive if rho is not equal to sigma. I think what I will do before lunch is just to prove that relative entropy is positive if rho isn't equal to sigma, and then after lunch we'll continue with some corollaries. So, so first of all, we can diagonalize sigma. Now, if it were the case that when we diagonalize sigma, rho were also diagonal, we'd kind of be in a world of classical physics and life would be easier. But in general, after we diagonalize sigma, rho is not diagonal. But we can let rho d equal a diagonal matrix, diagonal density matrix whose diagonal elements agree with rho. So rho d is obtained by rho by keeping the diagonal elements and replacing the off-diagonal elements by 0. Now, rho d is a density matrix. Because, well, first of all, the trace of rho d is the trace of rho, so it's 1, because rho d has the same diagonal matrix elements of rho. And secondly, rho was positive, but a positive matrix has positive diagonal elements. And therefore, rho d has positive diagonal elements, and therefore it's positive. Positive means non-negative. Some diagonal elements might be 0. So from this definition, you can write S of rho relative to sigma as the sum of two terms. One of them is S of rho d relative to sigma, and the other is S of rho d minus S of rho. And I'm going to show that they're both terms are non-negative, and therefore S of rho relative to sigma is non-negative. And the two proofs will make rather similar uses of convexity or concavity. So first of all, since rho d and sigma are both diagonal, so let's say sigma is a diagonal matrix whose diagonal elements I'll call Q1 up to Qd, and rho d is a diagonal matrix whose diagonal elements I'll call P1 up to Pd. So you can think of the Q's and P's as probability distributions. They're non-negative and they add up to 1. So these are classical probability distributions. So S of rho d relative to sigma is the sum of pi times log pi minus log qi. It's called the relative entropy or Kullback-Leibler divergence between the two probability distributions. And the fact that it's non-negative, or I loosely say it's positive, but strictly it's non-negative, is an important statement in probability theory and classical information theory. You can prove it as I said, using concavity or convexity. So we let pi of t be 1 minus t times qi plus t times pi, where t goes from 0 to 1. So pi of t is a probability distribution. It's a convex linear combination of probability distributions, so it's a probability distribution. To make that true, we kept t between 0 and 1. And then I let f of t be the sum of pi of t times log pi of t minus log qi. So I see that f of 0 is 0 because at t equals 0, pi equals qi, and the two terms cancel. It's also true that f dot of 0 is 0. If you differentiate pi of t with respect to t, and then set t equal to 0, you'll get 0 because these will cancel. If you differentiate this one with respect to t, what you'll get will be the sum over I of pi of t, except it'll be pi of 0. To get f dot of 0, if you differentiate this one, you get pi of 0, and then here you'll differentiate it, so you get pi dot of 0 over pi of 0. So this cancels, so you'll get d by dt of the sum over I of pi of t. But pi of t for all t was a probability distribution, so the sum was 1, and the derivative is 0. And finally, we want to take f double dot of t. And f double dot of t with a little bit of calculus is the sum over I of pi minus qi squared over pi of t. So it's equal to or greater than 0. So we have a function which is 0 at 0, and its first derivative is 0, its second derivative is non-negative. So therefore, f of 1 is non-negative. And that tells us what we wanted. F of 1 is the relative entropy between rho d and sigma. And if you look over the proof, you'll see it's strictly positive if rho d is not equal to sigma. Okay, well, we need one more proof. We claimed that S of rho d was equal to or bigger than S of rho. So, first of all, intuitively, rho is a density matrix. But to get from rho to rho d, you forgot some information. They have the same diagonal elements, which mean the same probabilities to be in one of the states given by the diagonal of rho d. But we've lost the correlations in the off-diagonal elements. So you might hope that losing those correlations increases the entropy. Anyway, we prove it by a similar argument to what I just told you. We let rho of t be t rho plus 1 minus t times rho d. And again, rho for t between 0 and 1. Rho of t is a density matrix. Well, it has to have trace 1, but it has trace 1 because rho and rho d both had trace 1. And it has to be non-negative, but it's non-negative because it's a linear combination with positive coefficients of positive matrices, or non-negative matrices. So rho is a density matrix. And now, what do we do? Well, we look at the function S of rho of t. And we find that d by dt of S of rho of t at t equals 0 is 0. So that just follows. You take the trace of rho of t log rho of t. I'll leave this as an exercise, but if you take this S of rho of t and this formula for rho of t, you'll find that the derivative with respect to t at t equals 0 is 0. If you find it confusing, there's a footnote in my lecture notes that might help. Actually, there's a fact which might help that we're going to need in a second anyway. We use the fact that the log of rho of t is the integral from 0 to infinity ds of 1 over s plus 1 minus 1 over s plus rho of t. This is true for numbers, so it's true for matrices. To prove it, you can diagonalize the matrix, and then it's true for each matrix element, so it's true for the matrix. So, well, this fact makes it easier to differentiate log rho of t. If you use this fact, you can compute that d squared dt squared of s of rho of t is minus the integral from 0 to infinity ds of the trace of rho 1 over s plus rho of t, rho times 1 over s plus rho of t. That's just by calculus. Using this formula for log rho of t, it's relatively straightforward to calculate those derivatives. I'm forgetting something, but okay. And this, the left-hand side is negative because it's the integral of the trace of b of t squared, where b is a positive operator. B is manifestly non-negative. So trace b squared is non-negative, and therefore the second derivative is non-negative, non-positive. So we have a function whose first derivative at the origin is 0 and its second derivative is everywhere non-positive. So we conclude that s of rho of 1 is equal to or less than s of rho of 0. But if we go back to the beginning, s of rho of 0 was s of rho d, and s of rho of 1 is s of rho. So we've proved well, we finished the proof of the fact that relative entropy is non-negative. So after lunch, we will make use of that fact a few times. But we'll stop here.